Space travel's evolving ambition to travel further and for longer poses many challenges. One of major concern is the limited volume and weight that can be transported out of Earth's gravitational field. To combat these constraints, inflatable systems have proven to allow similar weight and volume to conventional designs. The inflatable can be deployed in space, providing up to 3 times more volume than aluminium modules. NASA's Transhab was the first inflatable system considered for the International Space Station. However, due to cost limitations, it was never developed past physical testing. Like Blue Origin's space station, the habitat attempts to use humans' relationship with gravity on Earth to provide orientation. To maintain rigidity before and during launch in the B330, an interior support structure connects the life support systems to the airlock. However, this results in two-dimensional inflation, restricting the volume of the internal space. The internal support structure allows the pre-inflated module to be transported from Earth in the space shuttle. Although NASA's inflatable designs should support multi-axial orientation in microgravity, they instead follow earthbound notions of floor plates and walls, giving the illusion of up and down to their inhabitants. The Sierra Space Gateway uses Vectron fibers to provide a protective shell that can withstand both the vacuum of space and impacts from micrometeoroids. The International Space Station is the only permanent space habitation in orbit. Although it is due to be decommissioned in 2031, this design project speculates on its expansion via inflatable systems to explore how future space travel may be able to take humans to Mars. The ISS comprises of 3 main elements: a structural core, habitation and life support modules, solar panels. The habitation modules are primarily split by their order of deployment and ownership, with the Russian service module and functional cargo block being the first to be assembled, then the US nodes and research lab, and finally the Japanese experiment module. The Zvezda service module contains life support systems and sleeping harnesses. The functional cargo block contains storage space, electrical support, and docking mechanisms. The Unity module connects the US laboratories to the Russian modules. The Tranquility node contains an observation cupola, as well as a space toilet and exercise equipment. The research labs are where the astronauts spend most of their time. The Harmony module connects the research labs together and contains sleeping harnesses. Like the inflatable B330 and Transhab, the ISS uses Cartesian notions of horizontal and vertical movement. Although it helps astronauts find their way around the space station, it can be restrictive. The user group will be the astronauts staying on the ISS for prolonged periods of time. The crew of the ISS usually contains biologists, physical scientists, mathematicians, and engineers who each carry out research related to their specialism. Although large amounts of biological research are being carried out on the ISS, much of it is not related to the psychological issues of space travel. Instead, the astronauts are monitored and assessed back on Earth. This project will aim to provide new spaces to the station that will give novel methods of psychological research to improve health and well-being for long-distance space travel, where isolation and confinement are prevalent issues. Initial design development explored natural inflatable systems on Earth. The diving bell spider uses hydrophobic hairs on its abdomen to trap air bubbles below the water's surface. Analyzing the microscopic structure of the diving bell web revealed the variety of web types and how they can work together to trap the air bubbles after the spider has taken it underwater. Web A is a sheet material with hydrogel mucus that encases the air while allowing the diffusion of gases in and out. Web B anchors the sheet web to a support structure. Web C comprises of many smaller strands that work together as the primary structural component. The design development explored applying the web topologies to inflatable elements without the constraints of gravity. Dynamic systems were used to highlight the interaction between the fibers and inflatable elements. However, the freedom of simulating these elements without gravity made the test unsuccessful. To address this issue, the fibers were used as seam lines connecting the inflatables to one another. Considering that these inflatables could become the interior fabric of the proposal, initial tests into their augmentation in virtual reality were undertaken. This could allow the space station's occupants to forest bathe in virtual landscapes or experience the chaos of urban environments back on Earth. The monotone or harsh lighting on the ISS has been shown to contribute to sleep deprivation. Here, seam lines are emissive, which could provide a solution to repairing astronauts' circadian rhythms. When the inflatable web system was connected to the ISS, it was clear that additional constraints were needed to control the position of the post-inflated form. The developed proposal shows webbing connected to the ISS, indicative of the diving bell spider. Further analysis of the space station modularity was incorporated into the proposal, enabling a hard exterior shell to provide insulation and protection from micrometeoroids, while the soft, inflatable structure gives rise to multi-axial movement. The ISS common berthing mechanism will allow the modules to connect to the space station and to one another. The web seams will contain liquid to heat and cool the inflatables, creating a more haptic response of soft and hard surfaces when using the augmented reality.